Hello, viewers. Thank you again for joining me today. I feel so appreciated and honored. It is a continuation of magnetic effect of electric current, the second episode. Our objectives are, by the end of the lesson, we expect that the learner should be able to describe the nature of magnetic field patterns in a loop. 2. Describe the nature of magnetic field pattern in a solenoid. So in a loop and a solenoid. 3. State and explain factors affecting the strength of electromagnets. Finally, state applications of electromagnets. I expect you to at least state 3 applications of electromagnet. Feel most welcome, and let's continue. Hello, viewers. So let's start with this. What is a loop? Can you define a loop? Good trial. A loop is a piece of wire that has been bent into a circular path. So when such a wire is connected to source of power, then it produces magnetic fields around it. So in short, a loop is just a single turn. What? A single turn of a conductor. So what type of magnetic fields are formed on a loop? Follow me to the next slide. Alright, the magnetic fields formed in a loop are concentric, just as we saw in a straight conductor. They are circular on the loop. All parts of the loop contribute to magnetic fields. As you can see from figure B, we have very many concentric fields all around the loop. So each magnetic field at a particular point contribute to the overall magnetic field on the loop. So for easy drawing, we usually do not draw all the magnetic fields at any point or at all points. We only choose like 2 points and then draw magnetic fields. Have you noted one observation? The magnetic fields are in the same direction inside the loop. Hello? The magnetic fields have the same direction inside the loop. This leads to a second conclusion, that magnetic fields are strongest inside the loop than outside the loop. Right? Right. Alright, I want to feed you with this knowledge, a knowledge that you'll use for the rest of your life as a physicist. It is natural for current and magnetic field to exhibit this character. Which character am I talking about? Current and magnetic fields always meet at 90 degrees. If current was flowing from left to right, then magnetic field will form from down upwards. Put in another way, if current was flowing horizontally, then magnetic field form vertically on it. Simply put, current and magnetic fields always meet perpendicular to each other. Magnetic fields and current are perpendicular to each other. Simply put, but a very important point. Finally, the last time I'm talking about it, current and magnetic fields are always perpendicular to each other. So let's take an example of this loop drawn. As I stated earlier, you cannot draw fields all around the loop. I've only taken 2 points, the left side and the right side. This is how you draw the magnetic fields. They are concentric at any point. 2, they are perpendicular to the direction of current. And last, they are more concentrated inside the loop than outside the loop. So as current is flowing, magnetic field patterns forms on the loop, where more fields form inside the loop than outside the loop. Look at the diagram very carefully. You'll be able to see that inside the loop, magnetic field follow the same direction. This makes them to be strong inside the field. I pray that God may give you wisdom to see this. As you can see, magnetic fields, we are more interested with magnetic field inside the loop. You can see that we have very many of them. And you can use a compass needle to predict their direction or to show their direction. There are many versions of drawing magnetic fields pattern in a loop. So like this one here, it is a loop that is going through a cardboard. So you can see magnetic fields are parallel to each other and moving from one side to the other side. The same apply to figure B. The keynote here is for you to know that magnetic fields inside the loop are very many, and on the wire they form concentric circles, as you can see. So if you draw one concentric circle on the wire and then many fields inside the loop, then you'll be very correct. Asante. Okay, my objective in this slide is to help you determine the direction of magnetic field. I want to tell you what you already know. You already know that magnetic fields are concentric at any point of the loop. But in which direction do they face? We can use Fleming's right-hand grip rule to determine that. I want to say explicitly that there are two versions to this, but both of them are using the right hand. So let me start with Fleming's right-hand grip rule, first version. If you hold the loop at a given point using your right hand with your thumb pointing in the direction of current, then the four fingers will point in the direction of magnetic fields. You can see I'm just stating the right hand grip rule as we had stated it earlier. If you hold a conductor with your right hand with the thumb pointing the direction of current, then the four fingers point in the direction of magnetic field. You can do this at any particular point and you'll be able to determine the direction of what? Magnetic fields. Now, in our next episode, in our next slide, we are going to look at another version of this. Assumption made in this is that you are treating the loop as a straight conductor at any point. That's why you are using same rule as in straight conductor. I hope you are following, my dear listener. Direction of magnetic fields inside a loop. Right hand grip rule for a loop. This is the second version of stating right hand grip rule for a loop. If the fingers of the right hand curl along the loop in the direction of current, the thumb points in the direction of magnetic field inside the loop. Fingers curl around the loop in the direction of current. Then the thumb points the direction of magnetic field inside the loop. So this is specifically applied if you want to find the direction of magnetic fields inside the loop only inside the loop. So all you need to do is curl your fingers around the loop pointing in the direction of current, then the thumb automatically points in the direction of magnetic fields. Hello viewers, are you following? Okay, now let us change gears. Let us look at what we call a solenoid. What is a solenoid? A solenoid is made up of many loops of wire with a current going through. Solenoids are used to generate magnetic fields. Many loops form a solenoid. Remember, one turn is a loop. Very many turns of a conductor are now called a solenoid. So what type of magnetic fields are formed around a solenoid? Follow me to the next slide. Magnetic field patterns formed on the solenoid are similar to the magnetic field patterns formed on a bar magnet. So let me start with bar magnets. Look at the type of magnetic field patterns formed around a bar magnet. The fields always move from north to south. They form a complete loop. Look at figure B. A complete loop, just like going around a field. They form a complete loop. And the loop is facing either clockwise direction or anti-clockwise direction, just one particular direction. So outside the bar magnet, the fields move from north to south. But inside the magnet, fields move from south to north. This is just to make sure that they follow one direction. Just follow one loop and see it is flowing in a complete clockwise direction or flowing in a complete anti-clockwise direction. There is no way that the fields can oppose each other. They're either flowing in clockwise direction or anti-clockwise direction. So be very keen when you are drawing your arrows so that they make a complete loop following only one particular direction. And when I say one particular direction, I either mean clockwise or anti-clockwise. Since we've said that magnetic fields pattern of a solenoid are similar to that of a bar magnet, now let us see magnetic field patterns of solenoid, having seen those one of a bar magnet. Magnetic field patterns of a solenoid. Don't you see that they are very similar to that of a bar magnet? Fields are moving from north to south outside the solenoid. However, inside the solenoid, the fields are moving from south to north. Another observation, the fields inside the solenoid are very close to each other and are many numbers and are almost straight to each other. So because of these, Magnetic field's strength in a solenoid is very strong inside the solenoid. A question: why is it that magnetic field strength is highest inside the solenoid? Answer: this is because there are very many fields inside the solenoid. The fields are close to each other and the fields are almost uniform. That means they are straight. Are you following? All right, let's move on. I'm going to be very slow in this episode because there are some points that I want you to understand very well. So, the aim of this slide is to determine the direction of magnetic fields in a solenoid. However, you already know this. If you don't, let me remind you. If you have a solenoid, magnetic fields outside the solenoid moves from north to south, and inside the solenoid they move from south to north, such that they make a complete loop, just like in bar magnet. Now, the problem here is, how will you be able to tell which side is north and which side is south? That is when right-hand grip rule come in handy. So let us state right-hand grip rule, which will enable us to determine the polarity of the solenoid. So if you hold the conductor using your right hand with the fingers curling around the conductor in the direction of current, then the thumb points in the direction of north of the solenoid. I always say, put the rules in your own words. Just understand the concept and then put the concept in your own words. These are a rule, not a law. So if the coil carrying current is held in the right hand such that the fingers encircles the loops while pointing in the direction of current, the thumb points in the direction of North Pole. I want you to try and put in your own words. All right. Right hand rule for solenoid. If I put it in my own words and say, if I hold a conductor using my right hand with my four fingers curling in the direction of current on the solenoid, then the thumb points in the direction of north. If I hold a conductor using my right hand with my four fingers pointing the direction of current, my thumb will point in the direction of north. Thank you. Okay, there are two rules that you can employ to determine the polarity of a solenoid. The first one, we have already looked at it, that is right-hand grip rule. Now, the second rule is called clock rule. Other books call it clockwise and clockwise rule. So let us look at clock rule. The clock rule states, if the direction of current in the coil as observed from one end is clockwise, the end is south. And if the current is anticlockwise, the end is north pole. So all you need to do is to view how current flows from a given end. If the current is clockwise, then that side is a south pole. But if current is flowing in anti-clockwise direction, then that side is a north pole. All right. I want you to apply the clock rule to determine the polarity of the solenoid given below. All you need to do is to imagine looking at the solenoid from one end. If current is flowing in clockwise direction, then that side is a south pole. If current is flowing in anti-clockwise direction, then that side is a north pole. How do you know that current is flowing clockwise? Remember, clockwise direction is when something is moving from, let's say, left hand towards the right hand. And clockwise is when something is moving from right hand side towards the left hand side. So if you view current on the loop at the end of the coil or the solenoid, and you realize that current is flowing from right to left, then that is anti-clockwise, and that need to be a north pole. But if current is flowing from left to right, then that is clockwise, and that side is the south pole. Take your time and figure this out. It is an important point to remember as we move on. To determine the magnetic field patterns in a solenoid in the laboratory, procedure: create loops through a hard cardboard, sprinkle some iron filings on the cardboard, join the loops to a source of power, switch on the current, tap gently the cardboard to align the iron filings. So you'll realize that they form concentric circles around the loop as shown in the figure. What is an electromagnet? An electromagnet is a magnet made from current flowing inside a solenoid. So the solenoid that we've seen in the previous slides form a magnet. That type of a magnet is called an electromagnet, a magnet made from electricity. Now, what determines the strength of an electromagnet? There are four factors that determine the strength of an electromagnet. One is the number of turns on the solenoid. And I'm not talking about the number of coil. Remember, the whole of that solenoid is called a coil. So some students make this misconception of stating that the number of coils. It's not the number of coils, but the number of turns in the coil. Point number two, the current. So the current will also determine the electromagnetic strength. Three, the length of the coil. So how long the coil is determine the strength of electromagnet. Last, the type of conductor. Sometimes we use a straight conductor to form an electromagnet, and sometimes we use a U-shaped conductor to form electromagnet. So the shape of the core of the conductor will determine the strength of an electromagnet. Now let us see these 4 points individually in the next episode. Okay, how does the number of turns determine the strength of an electromagnet? The higher the number of turns per unit length, the stronger the electromagnet. Magnetic fields are produced in each turn. So the more the turns, the more the magnetic fields, the stronger the electromagnet. So as you can see from figure A, if you have very many turns, that electromagnet will be able to attract very many pins. But if you have few turns, the electromagnet will attract few pins. The more the turns, the stronger the electromagnet. Another way that you can increase the strength of an electromagnet is by increasing the current in the solenoid. So the higher the current, the stronger the electromagnet. So if you use one cell and make an electromagnet as shown in figure A, it will be able to attract few paper clips. If you use many cells, it will be able to attract many clips. Conclusion: the more the number of cells, the higher the current that flows, and the stronger the electromagnet become. So the higher the current, the stronger the electromagnet. Do you want to create a stronger electromagnet? Then instead of using a bar-shaped electromagnet, use a U-shaped electromagnet. If the core is U-shaped, it is like using two bar-shaped electromagnets. Can't you see from the diagram? So this one make a U-shaped electromagnet stronger. So you want to have a stronger electromagnet, instead of using a bar-shaped one, use a U-shaped one. Okay, other factors affecting the strength of electromagnets include: 1. Presence of a core. Without a core, the electromagnet will not be very strong. With the presence of a core, the electromagnet becomes very strong. Why? The core concentrates magnetic fields inside the solenoid, making the field to be stronger. So the last factor that affects strength of electromagnets is the length of the core. It is better to have many turns on a short core than the same amount of turns in a long core. So the shorter the core, the stronger the electromagnet. So in summary, 4 points, in fact 5 points, that determine the strength of electromagnet. 1 is current. The higher the current, the stronger the electromagnet. 2, the number of turns. And as I said, don't use the number of coils. So the more the number of turns, the stronger the electromagnet. 3 is the shape of the core. The U-shaped core creates a stronger electromagnet as compared to a bar shape. 4 is the length of the core. The shorter the length of the core, the stronger the electromagnet. 5, which is related to 3, absence or presence of the core. With the presence of the core, the electromagnet becomes stronger. With the absence of the core, the electromagnet becomes weak. Thank you so much. Mpenzi msikilizaji, na kushukuru sana kwa kuwa nami hadi tamati. I want to conclude by giving examples of application of electromagnets, which include cranes. Cranes are used in ports, just like Mombasa ports, to lift objects from the ships to the port. 2, They can be used in making motors. 3. They create generators. 4. Can be used to make hard disk. 5. Loudspeakers. 6. Relays. 7. Electric bells. There are very many applications. These are just examples. Remember to at least quote or state 2. Motors, generators, loudspeakers, electric bells. Now, please, there is a last important request that I want to make. Make sure that you subscribe. Make sure that you refer this channel to other friends of yours. Thank you so much. God bless you. God bless you. God bless you. God bless you.